Good day everyone, we are Group 7. I'm Engine Cadet Peralta,
Engine Cadet Cabarlo,
Engine Cadet Pasalo,
Engine Cadet Rufino.
Engine Cadet Ancheta.
Today, we will discuss the use of alternatives fuel in shipping to comply SOx, NOx, and carbon emission requirements. The shipping industry is facing increasing pressure to reduce its environmental footprint, particularly in terms of sulfur oxide and nitrous oxide and carbon emission to comply with estrogen regulations set by International Maritime Organization and other governing bodies. The industry is actively exploring and implementing alternative fuel. This shifts away from the traditional heavy fuel oil is driven by the need to mitigate air pollution, improve public health, and combat climate change. The shipping industry is essential for global trade, but is also a major source of air pollution. Ships emit sulfur oxide and nitrogen oxide and carbon oxide, which harm both air quality and environment.
To combat this, the International Maritime Organization introduced MARPOL Annex 6, the Energy Efficiency Design Index, and the Carbon Intensity Indicator to regulate and reduce emission.
The Energy Efficiency Design Index, EEDI, is conceived as an IMO mandatory instrument to be calculated and made as available information for new ships from 2013. EEDI represents the amount of CO2 in grams emitted when transporting one deadweight tonnage of cargo 1 nautical mile.
With regard to the G engines, there the essence is that we utilize a lower RPM. We have actually always been able to utilize lower RPMs by using our layout diagram, which is very flexible layout principles. What we do now with the G engines is that we push the whole diagram a little to the left. Thereby we get lower RPMs, thereby we can get the better efficiency of the propeller. Going from the S engine to a G engine, that means extending the stroke to bore ratio, thereby we get an engine with a longer stroke with a lower RPM. This gives also the better efficiency of the propeller.
The G-type engine has a design that follows the principles of MAN Diesel and Turbo's large-bore S-type Mark 9 engine, but whose ultra-long stroke enables the reduction of engine speed, thereby paving the way for ship designs of unprecedented high efficiency. Using the latest aft-hull designs that allow the use of larger and more efficient propellers, the new MAN B&W G-type engines will enable tankers and bulk carriers to operate at even lower speeds and fully exploit the savings potential this new technology offers. The development of the Capel propeller portfolio is the result of a concentrated body of work lasting over 2 decades. The Capel propeller minimizes the flow of water over each propeller tip, increasing the total efficiency of the propellers compared to conventional units. In combination with the G-type engine, Capel propellers can reduce CO2 emissions and fuel consumption by up to 10%. The most efficient way to increase the total efficiency of a ship with a 2-stroke engine is to utilize the engine's waste heat. This waste heat is primarily collected from the engine's exhaust gas. The MAN Diesel and Turbo developed Waste Heat Recovery, or WHR system, utilizes the exhaust gas temperature to heat up steam, which in turn drives an ultra-efficient steam turbine. When waste heat recovery is combined with NOx reduction methods, such as an EGR system, total efficiency can be significantly raised. The MAN Diesel and Turbo developed exhaust gas recirculation, or EGR system, is based on the principle of reintroducing a part of the exhaust gas back into the cylinder, thereby reducing NOx formation by lowering the peak temperature in the cylinder. In this way, up to 40% of the exhaust gas can be circulated through the EGR string of the system. The exhaust gas in the EGR string is first cooled down from 200 to 500 degrees Celsius to around 80 degrees Celsius by means of a pre-scrubber that absorbs and neutralizes sulfur dioxides and traps particles. From the scrubber unit, the exhaust gas is led through a water mist catcher that traps water droplets and prevents water carryover before the exhaust gas can be reintroduced into the scavenge air receiver. Tests of EGR units have displayed considerable reductions in NOx, with just a low penalty in terms of overall system efficiency. MAN Diesel and Turbo consistently invests in its research and development program to reduce the environmental footprint of its existing engines, introduces new, greener engines, and develops ever cleaner technologies that seamlessly integrate with its product portfolio.
What is Carbon Intensity Indicator, CII? Under MARPOL, International Convention for the Prevention of Pollution from Ships, the term carbon intensity indicator refers to a specific metric used to assess the energy efficiency and carbon emissions performance of ships. The International Maritime Organization, IMO, which governs MARPOL, has introduced regulations aimed at reducing greenhouse gas (GHG) emissions from international shipping. The carbon intensity indicator is a measure of a ship's energy efficiency in relation to the amount of CO2 emissions produced per unit of transport work. Ships subject to MARPOL regulations are required to report their carbon intensity indicator values and demonstrate compliance with the EEDI and SEEMP requirements. The carbon intensity indicators enable monitoring, benchmarking, and improvement of ships' energy efficiency and carbon emissions performance over time.
A key solution is switching to alternative fuels. But what are they? How do they work? What challenges do they bring?
We will discuss hydrogen, ammonia, biofuels, and methanol, exploring their benefits, challenges, and real-world application.
So let's begin. Hydrogen and ammonia as alternative fuels. Hydrogen is a promising zero-emission fuel. When used in fuel cells, it produces only water vapor, making it environmentally friendly. However, it is a high production cost and storage difficulties are major challenges.
Ammonia is a promising alternative fuel with a high energy density and low viscosity, making it suitable for long-range shipping operations. Green ammonia, produced using renewable energy sources, is a carbon-free fuel. However, ammonia is a highly toxic and requires specialized handling and storage facilities. So ammonia, which is produced from hydrogen, is easier to store and transport. It can be used in modified engines or fuel cells, but its toxicity raises safety concerns.
I bet you didn't know that ammonia could power the ships of tomorrow. Let's dive in. So, ammonia engines are... What's the big deal? Unlike traditional fuel, ammonia doesn't produce CO2 when burned. That's right, zero carbon emissions. Plus, it's abundant and can be produced using renewable energy. Imagine a world where our cargo ships glide through the seas without harming the planet. Cool, right? And there's more. Ammonia engines are efficient and can be retrofitted into existing ships, so this means we don't need to build a whole new fleet. Just a switch, and we're good to go. In short, ammonia can help us cut down shipping emissions significantly. It's a game changer for our oceans and the planet. So, next time you see a ship, think about the cleaner, greener future it could be part of. Ready to ride the wave of change?
Biofuels derived from renewable sources like agricultural waste and algae offer a potential pathways to reduce GHG emission. They can be blended with conventional fuels or used as a standalone fuel. Biofuel have the potential to significantly reduce carbon emission, but their production and supply chain are still under development.
In addition, methanol is a liquid fuel that can be produced from natural gas, coal, or renewable sources. It offers significant reduction in SOx, NOx, and particulate matter emissions compared to HFO. Methanol can be used in existing engines with modification, and it is relatively easy to store and transport.
What's something people don't know about shipping? It's a huge contributor to global emissions. But wait, there's hope on the horizon. Introducing methanol fuel, a revolutionary way to power our ships that's cleaner and greener. Created by combining air and green hydrogen, methanol captures carbon dioxide from the atmosphere, turning it into a clean-burning fuel source. Companies like Hapag-Lloyd are already embracing methanol, proving its practicality and cost-effectiveness. This shift could reduce emissions by up to 70%, driving us toward a greener future. And guess what? Methanol is compatible with many existing engines, making the switch seamless and financially viable. What are your thoughts on this groundbreaking technology?
Biofuel, derived from plants, oil, and waste, are a viable alternative since they can be blended with traditional fuels, requiring little to no engine modifications.
Methanol, produced from biomass or captured CO2, is gaining popularity. It remains liquid at room temperature, making storage and transport easier than hydrogen or ammonia.
One key development is Mike's investment in methanol-powered vessels. The company plans to deploy a fleet powered by methanol, setting a precedent for the industry.
Furthermore, biofuels and methanol offer a practical transition for shipping companies hesitant to adopt more complex alternatives. Their lower carbon footprint makes them an attractive choice for near-term sustainability.
So are these fuel widely available? Infrastructure and supply chain limitations still pose challenges, but advancement in production and distribution are making them more accessible.
Industry initiatives and future outlook. Shipping giants like Hapag-Lloyd, Maersk, and CMA, CGM, and adopting butane and dual fuel vessels, paving the way for industry-wide change.
So the IMO 2023 strategies promotes zero or near zero GHG fuels, with increased investment in research and infrastructure to support this transition.
One challenge remains cost. Alternative fuels are still more expensive than traditional marine fuels, but technological advancement are expected to drive costs down.
Public-private partnership and government incentive will play a crucial role in accelerating the transition. Countries like Japan and Norway are already investing heavily in green shipping technologies.
So what's next for the industry? Expert predicts that a combination of these alternative fuels will be used to meet varying operational needs.
Alternative fuels are essential for reducing shipping emissions. Hydrogen, ammonia, biofuels, and methanol each have their advantages and challenges, but all contribute to a sustainable future.
Regulatory bodies and private companies must work together to improve infrastructure, safety, standards, and affordability to make these fuels widely adopted.
As future marine engineers, we have a role to play in advocating for and implementing these sustainable technologies in our industry.
It is up to us to stay informed, innovate, and push for cleaner shipping practices that will benefit both the environmental and the economy.
So a greener future starts with awareness, commitment, and action. So together we can drive maritime industry toward sustainability.
So, in conclusion, the shipping industry is at a crossroads facing the needs to transition to alternative fuels to comply with the environmental regulation and reduce its impact on the planet. While challenges remain in the industry is actively exploring and implementing a range of alternative fuels, each with its own advantage and disadvantage, the future of shipping will likely involve a portfolio of alternative fuels tailored to specific ships types, routes, and operational requirements. Collaboration between industry stakeholders, governments, and research institutions will be crucial to accelerate transition to a more sustainable and environmentally friendly shipping industry.
A greener future starts with us.